Hi, my name is Elza Moore. I'm an undergraduate student at Scripps College. I'm a senior and I'm a math major. I'll be presenting on this paper called Hopf, Algebras, and Markov Chains, Two Examples and a Theory. The paper is by Persi Diaconis, C.Y. Amy Pong, and Arun Ram. I'll be providing kind of an introduction to what you need to know if you want to kind of dip your toe into the water of reading this paper yourself. I'm not going to dive too in depth with it. The paper is very detailed and not way too much to cover in a short presentation such as this. Also way too dense for me to understand all of it. Here we go. So I'm going to start by kind of going over the general idea of the paper first so that you can get an idea of just what we're kind of dealing with here, and that can be in the back of your head while we're defining our terms so that you kind of know what our motivation is in defining all of these terms. So the basic idea of the paper is that we have some Hopf algebra, which is a type of algebra that we'll go over later, and some operation called Hopf square. And basically the Hopf square has a natural basis, also known as the standard basis, and the coefficients of that standard basis can be interpreted as a Markov chain. And that can give us a lot of different ways to kind of deal with these Markov chains and probabilistic processes. So let's start by defining what a Markov chain is. So you see here, we have a Markov chain is defined as this kind of set of random states here, where our xn is kind of our what state of some system we're in at our nth trial. So a Markov chain is a probabilistic process. It's a random process. And in order to describe a Markov chain, you need a state space, which for a finite Markov or discrete Markov chain, the state space is a finite collection of states that we can label using positive real values or positive integer values in this case. I decided to start at 1 just to make this example a bit simpler, although you can start at 0 as well. And so you also need a transition matrix, which I've given an example of what a transition matrix might look like. So you have this matrix P that the rows are labeled with the first state to the ith state, and the columns are labeled from the first state to the jth state. And each entry in the transition matrix is some probability that, given that you're in a certain state right now, or when you look at the chain, that the next place you go will be some other state. So if you can see here, you have the probability that if you start in state 1, you'll stay in state 1, all the way up to the probability that if you start in state 1, you'll go to state J. So stay in state 1, go to state 1, stay in state 1, go to state 2. So all of those probabilities are there, and each row kind of corresponds to a specific state that you start in, and each entry in that row is the probability that, given you start in that state, you'll go to each other state up to the jth state. So I've shown that example here with this matrix here that goes up to from up to the ijth probability. So here, I've said that the xn in our Markov chain equals the state of the Markov chain at our nth trial. So if you want to find out kind of what the expected value for the next place is, you can apply the transition matrix to your current state, and you'll get the value for the next state. So that's how this works. And you can do a ton of things with these. You can model a lot of random systems with them, and they're super helpful and super useful for a lot of probability theory, where you don't care about any of the history of where you've been. You only care about where you are, and you want to figure out where you're going to go. And surprisingly, it's very accurate in modeling all sorts of systems, despite only seeming kind of simple. So now I'm kind of going to go into, I'm going to leave Markov chains behind. We'll come back to it, but I'm going to kind of go into Hopf algebras and trying to describe that. So you may remember from our text or from representation theory, if you've taken it, if you're in our class, then you've taken it, but you might not be. So you might remember that an algebra is a map or a function R to A, where R is a commutative ring with unity and A is just a ring with unity. It doesn't have to be commutative. So in this map preserves the identity. So the identity in R maps to the identity in A, and the image of R in A is in the center of A. So that's an algebra more generally. So if we want to talk about Hopf algebras, we need to know that. And another thing we need to know is the concept of bilinearity, which is a property of algebras generally, but it's really important in Hopf algebras specifically. So a bilinear map is a map A cross A to F. So A is a vector space and F is a field. So you're crossing two vector spaces, and what you're getting is a field. So I figured I'd give an example because this kind of cleared up what a bilinear operation or a bilinear map is. So an example of a bilinear map is the dot product between vectors. So as you can see here, you take two vectors, you do some operation, which we've defined as the dot product, and you get a value that's in the real numbers, which is a field. So now we're going to talk about Hopf algebras. I've put a little bunny there because Hopf sounds like hop to me, so I thought it was a little cute. The bunny's saying hop, hop. A Hopf algebra is the same idea. So it's an algebra. So you have an associative unital algebra. But the only difference with a Hopf algebra is that a Hopf algebra is a bialgebra. So that means that it has a product and it has a co-product, or it has an algebra and a co-algebra. So I'm not going to talk about algebras and co-algebras, but I'll talk about product and co-product because they're pretty important. If you want to know more, there's a lot of sources in the paper that go really deep. The paper doesn't go super deep, but it does have a pretty good introduction. The product is this mapping of the tensor product of our Hopf algebra with itself to the Hopf algebra, and the co-product is kind of the reverse of this. So it's a mapping of the Hopf algebra to the tensor product of the Hopf algebra with itself. So I'm going to go a little more in depth with this idea because it can be a bit confusing. So more generally, I'm going to say that the product of an algebra is a binary operation on A, so that A and this operation with itself maps it to A. So I've defined here kind of, you take these two values that are in A and you get A times, A acting with B, and this is this operation defined on A. So and so if we talk about the Hopf algebra as a graph, with one of the arrows being the product, I'm calling it mu, and so that arrow is kind of going that way in the graph, and the co-product delta is the arrow of the same graph, just reversed. So the product is this mapping that goes this way, and then the co-product is this mapping that goes the other way, and they're not just reversed because anytime you're dealing with maps, you can't always just kind of take the same thing and bring it in the opposite direction. So it does actually change things about what you're looking at when you reverse it in a lot of cases. So the paper uses something called Sweedler's sigma notation to talk about this. So I figured I'd go over it because it's a little confusing. But In this notation, the coproduct is described by a linear combination of simple tensors. So I'll show you an example here that is in the paper that says this delta, the coproduct of a Hopf algebra H, can be described as delta that takes a value x, and it does this kind of summation of the simple tensors, the linear combination of these simple tensors. And in the text, it says that the coproduct is co-associative. I'm not going to go into what that means, but it's kind of important, but not, it's too detailed for today. So another important thing that you can do with Hopf algebras is this idea of the Hopf square, which is the mapping from the Hopf algebra to itself. The paper both writes it as this kind of x to the bracket 2 power, and it also writes it as this gamma to the 2 power. They swap it out periodically, probably just for convenience of notation. I will mostly only use the x to the 2 bracket notation. If I use the other one, it was a mistake, just for simplicity's sake. So yeah, you can see it's this map M delta that takes H to itself. So yeah, it's called the Hopf square. So yeah, now we can get back to the big idea. Now that we kind of have all of those definitions out of the way, we can get back to the big idea, which is, how can we interpret the Hopf square as a Markov chain? So we say here we can interpret the Hopf square as a Markov chain when the coefficients of this Hopf square are non-negative real numbers for B and B. So B is the basis of H. So you take some basis vector of H and you put it into this Hopf square map. And when the coefficients of this map are non-negative real numbers, you can interpret it as a Markov chain. So to go a bit more in depth with that, so this will happen quite often. Well, this will almost always be true for combinatorial Hopf algebras, which I'm not 100% sure what that is, but it's a thing. So this will usually be true for what the paper calls combinatorial Hopf algebras. But for free associative algebras, it's even cleaner than that. It's even nicer than that. Because you can say that the coefficients sum to 2 to the degree of B, regardless of what basis vector you're putting into it. So you get this function, which you can see here, which forms a Markov transition matrix on basis elements of degree n. So yeah, hopefully that you can understand that. So yeah, why do we care? Why is this relevant to our class? So, you know, kind of the point of all this is that when you have these Hopf algebras and you can describe Markov chains in this way, or you can describe Hopf algebras as Markov chains, there are a lot of operations that you can do on them. Specifically in this paper, it really focuses on eigenfunctions and doing operations with left eigenfunctions and right eigenfunctions to kind of gain information about the system that you're looking at. And that's a lot easier when you can look at things as Markov chain, when you can look at things as Hopf algebras and represent them in the form of matrices. So yeah, that's all. Thank you so much, and have a wonderful day.